1, 2, 3. Is there a sound recorded? Yeah, sound works. Okay, so dear ladies and gentlemen, I'm starting finally my stream. I have a new camera and I have good posters there, FST project. And that's actually a thing that I wanted to do for more than a year, to have nice streams when we discuss articles. And I have prepared to some extent one article that is a little bit coincides with my PhD studies. So let's jump to the discussion of science finally after such a long time. Okay, so so here there is an article which was published in 2008. It's called From Mott State to Superconductivity in Tantalum disulfide, and 1T is the phase of tantalum disulfide. That's a rather famous article. We can check. Let's check. It has 1,400 citations, 1,300 citations. So it's valuable for scientific community. And today I will show you how my app, which I'm developing right now, can help, for example, someone to read it. For example, it helped me to understand what happens in this article and understood it to some extent. So you can ask some questions here in this window for questions. No, was this window which is at the left side of the screen. So that's what's going to be in nearly 1.5 hours. I think that's enough time for me to discuss everything here. And that's the article, that's our application, and this is a collection of articles about TMDCs, or transitional metal dichalcogenides. So let's jump to the main conclusion of the article, because that's the most important thing, and later we will discuss some details about it. And yeah, I'm not expert in this topic, but I studied this article for around 10 hours total in my life. So I think that's enough to propose a stream and to hear some comments. Of course, there will be most likely no comments, but who knows? I promoted it 10 minutes ago, the stream. So the takeaway of this article is that there is such a special model, tantalum disulfide. Of course, it's well-known material for more than 50 years already, and there are a lot of other articles about it, but this article gave us this plot of like resistivity as a function of temperature and pressure. We will discuss this plot later, and this is the main plot of this article. In particular case, if we fix a pressure, then they measured a lot of resistivities of this material at different pressures, and here we can see, I'll just need to zoom it in. Sorry. Yeah, so now it's better. So that's the plot of the resistivity. And we can see that it's a non-linear one. It has some jumps of resistivity. One jump is here, another is here, and it's very much related to this plot where colors are used to show the resistivity. And here, for example, we see the change from metallic state where resistivity is not that big to some state with like resistivity which is much higher. It's a logarithmic plot, right? So if we have this increases of resistivity, then it means it increased not 10 times, but let's say 8 or 5 times, which is a really big change of resistivity. And then here we have some hysteresis. They don't comment actually hysteresis in this article, but we can try to guess together what is the reason of it and which role does it play. It's actually really strange. I don't know any explanation of the hysteresis, neither of other phenomena, but I know what's written in the article, so we can discuss it. So here there is this transition to the Mott state. Okay. Sorry, I think I was a little bit wrong. That we should think about this plot as motion from vertical line. And yeah, if we go along this vertical line, then we get this plot. That's the first point where we go to NC-CDV phase, which I will explain later. What does it mean? And here we go to the state of Mott insulator. And here in the article, it's not explained what is meant by Mott insulator, so we need to read some references. But I know to some extent what is a Mott insulator, so I will comment later. But before you watch, I think it's a good idea to point out the main conclusion of the article, so if people don't need this statement or they want to hear some other scientific streams, they can switch to other scientific streams. So this is the main result of the article. Also, by the way, the advantage of this app is that we can modify easily everything what is here. This is the collection of main formulas, but right now I'm not going to do it because app is not finished, so I'm not sure if it modifies or there will be some bugs. But that's the main plot. Then it's also said that resistivity depends on the distribution of electrons, and we have different distributions of them. They can be not ordered or they can be partially ordered. And finally, in the insulating state, they are ordered in David stars fully, as will be discussed further. And this arrangement of electrons is assumed as the reason of different value of the resistivity. That's one example of the value if we go low along the vertical line. Basically, that's all. That's not an important plot. They here just want to connect the resistivity with the Coulomb energy. And okay, they claim that there could be several such David stars of electrons in one unit cell. Or maybe that's not the case, but that's how I understood it after reading chapter about it. And it's a very unclear chapter, so I don't think that's really important. I don't see any conclusion, like reasonable conclusion from it, but they claim that this is the region which is which plays role in the experimental measurement. And okay, because of some reasons they do the calculations and then they claim that this calculation can be related to explanations of some phase transitions, but I don't think that that's a good argument. That's a very unclear statement, and they also don't tell much about the calculation, which they do. So let's not think about this plot. And this plot is the same, but along the horizontal direction. And along the horizontal direction we fix temperature 6 Kelvin, so it's approximately somewhere here, this line. And that's actually a wrong plot, because they do like this. They say, oh, superconducting temperature is like 5 Kelvin, but let's multiply it by 10 and get like around 50 Kelvin. I'm not sure that it's like correct to do like this, but that's how they did it. And if they didn't do it, then we would not see at all this region of superconductivity because of the scale. So we just need to keep in mind that this plot is on strange scale, where part of it is rescaled and other parts are maybe not rescaled, because they haven't ever said about rescaling of other parts. And if we go along this line, along the pressure, then that's how resistivity changed. We start with this very insulating state, then we have a sharp decrease of the resistivity to some not big but not little constant, and then not so sharp decrease to approximately a constant value in metal state. And that's what happens. That's the first sharp decrease, and then second one, which is not that sharp. So that's the conclusion, and that's experimental article. So we will not have okay, there is only one formula. Okay, there are two formulas. The one formula is for Mott insulating Hamiltonian, which is well known, which they could even not write. I don't know why did they write it. Okay, because there are some parameters, and then they share the ideas how pressure and temperature, okay, maybe only pressure, how pressure changes that parameters. And the second formula is used to obtain this strange plot, which is not really connected to anything else. I mean, okay, they claim that it's connected, but I don't see how this is connected. And that's the structure of the article, but unfortunately it's a little bit broken. Yeah, they have just several paragraphs. It's like, as I showed you recently, it's a 6-page article. So we will have just 1 hour of discussion of it. Here they discuss just general motivation, then they discuss the results, and that's the main result, by the way. Then they share the ideas about these phases. Sometimes they repeat the statements before, but sometimes they share their thoughts. They don't use any formulas. Some ideas look a little bit abstract, and they have a lot of references. So if you need, you can read the references. But unfortunately, this button, where is this button? Okay, there was a button here, download all cited papers, and it was working to some extent. It was downloading something. Okay, continue. Okay, so we have download all 20 papers. So if I put that paper from archive, it should download all the cited papers, and that's how it could be way more easier to understand what do they mean by their citations. But right now this button is not working, and of course we are all lazy to Google each paper one by one. So we will not learn what do they mean by their citations. So our app, just to remind you, is the solution for this problem of the stupid citations where they just cite, and then you can't understand anything. Okay, what I wanted to do, I wanted to open finally the PDF with my comments, and right now I see that my face is a little bit not on the place where I want it to be, but okay, that's already the change for new stream. So let's go carefully line by line, and I will comment what I think about it, but maybe I need to move to this side to have more space. So of course I don't remember anything, a lot of things here by heart, because there are a lot of information. So here in the abstract they say that like, okay, that's the general motivation is that if we so there are different phenomena in condensed matter. One phenomena which is very well famous is the superconductivity, where we have like paired electrons. If it's okay, in any superconductivity, electrons are paired, just there are different pairings. But anyway, if you cool system to the low temperatures, then in sometimes there is this special superconductivity, which is well known for maybe already 80 or 90 years. Okay, I forgot the date when it was discovered, but at least for 70 years. And here this superconductivity is present as announced from the experimental plot. Another effect that is also relatively well known is the charge density wave state. And usually this charge density wave state occurs in materials which has little dimension, like one-dimensional material, and here we have a two-dimensional material. So right now in the top of my head I don't remember how it works for two-dimensional material, but of course I have some article here to help me. Unfortunately, this app is not working as good as I want it to work. So, okay, let's use the old method when we just do the table of contents scrolling. I wanted to detach this thing and open this article on the origin of charge density wave. Dun, dun, dun. I mean, if I click here, I see that there are these articles. Okay, if I click like this, open file, then I open file, then maybe I can click PDF, and it tells me that no, I need to use PDF clicks. And that's what happens when you don't fix bugs, but fortunately I don't have much. There it is. Here's this paper. I don't have much resources to do the programming. I need to do physics, and that's very important. So that's more important for me to do physics than to do programming right now. Okay, let's keep this thing open, and let's use finally our app to have some advantages. And so I wanted to tell you something more about charge density wave. I claimed that typically charge density wave is derived in the one-dimensional case, and I just wanted to comment a little bit why is it so and what to do in two-dimensional case. And this paper which I opened right now on the origin of charge density wave in selected layer transition metal dichalcogenides by Rusnager. So this paper gives some hints about this. And this is the typical theory of parallel transition, which is the transition to charge density wave state. It has some interesting ideas behind it, that we have some distortions. What if we have a periodic distortion? Then we will have a modulation of electrons, and that's more energetically favorable than to having no distortion. And not to be very diverged, I just wanted to make a claim and not really dive into this direction, but somewhere here in this formula lies the answer that about the dimensionality, that if you have this susceptibility divergent, then you will have a transition to some special state, and in exotic materials it's possible to find such configurations of energies of wave vector and Fermi distribution to To get the divergence even in two-dimensional system. There is the plot somewhere here. There should be a plot. Okay, the plot is not in this article, but in another article, which is in my project about purely chart density wave. Maybe we will need this Rosnager's paper, so let it be here, and let's go back. And I wanted to know that that's the advantage of our app, that you don't need to scroll, and that's the idea why I'm developing it, not to scroll, but having everything in front of you and enjoying doing science way more. There are two special states, the superconducting state and the chart density wave state. And in scope of chart density wave state, there are a lot of them. For example, one like a measured state, non-commeasured state. I don't actually understand right now yet what is this commeasurability or non-commeasurability, but there are some images, so I will tell later what is meant by it. Just want to say that in scope of chart density wave state, as I showed you on the plot of resistivity, there could be a lot of resistivity, and we say that's a Mott state of Mott insulator. What is written here, that this Mott insulator state melts to chart density wave state. Okay, they call it textured chart density wave state, but I think that both of them actually are in scope of chart density wave, and Mott phase is not a special phase, but just a part of chart density wave state. Okay, the reason is that like here they even show explicitly that in metal state you have okay, I don't know what they mean. Maybe they mean like homogeneous model, and when we, for example, have such temperatures and when we decrease pressure, then okay, it's not clear why. They have some guesses why, but they're more philosophical guesses. So such David stars appear, and then there are more David stars, and here there are just only David stars of electrons. So electrons are localized in such sites which form David stars. That's why I think that it's like still a part of chart density wave state. I don't know. Okay, maybe it means that, yeah, I didn't comment. I actually commented many things here. That's also the advantage of my app, that you can easily add comments here and you don't need to write much. You like write the article itself. You can just put your comments and see your comments, then modify if you need them later. Okay. What is written here? Okay, they report that they found the superconductivity. I need to believe them because I don't know what happened before. They also say some electronic phase separations, coulombically frustrated phase, and commeasurability driven phase. I have truly no idea what do they mean by these words. For me, it's just abstract words. Maybe in some cited literature, some authors use similar words, but for me, this doesn't mean much. Let's check if we didn't forget anything. What is announced in the abstract? No, basically, yes. They just looked at the phases, used their special advanced techniques of measurement of resistivity, got a lot of resistivity, and then gave us some plots. That's all. Why are they interested in exactly this material? Because it has a lot of phases. That's why it's more interesting, that we can find out how change of one parameter brings material from one phase to another. Will it be really useful for some applications? I haven't heard any good argument. They of course claim that this material is used for fast switchers. Is it really used or not? I don't know. I haven't seen anyone who was really developing something really practical. There were people who just were studying this material but not really trying to make better better memory devices, but maybe they are there. I just didn't meet them personally. So this material right now is in scope of purely theoretical interest, that it has different phases. Let's ask why we have different phases, why if we change one parameter we can get from one phase to another. Right now I don't know some good explanation of this theory, but also it's not really a thing that I should be focused much. It's just the overview of general properties of tantalum disulfide. Also, there is a good question: what if we take another two-dimensional material, not titanium disulfide, but one of many others that is two-dimensional? I don't know how much this ideas of this existence of phases is applicable for them. Okay, let's go finally to the article. Yeah, they claim for some reason that there are some electronic instabilities for low-dimensional systems. Well, that's what I said about the charge density wave. Maybe they mean this, and actually, so I know the answer on this question, which I wrote a very long time ago. Okay, I don't know the answer; it's still not answered, but the answer is somewhere here, is in Rosnagel's paper, where he was calculating the susceptibility. There is also a book by Gruner, actually, so maybe book by Gruner is the better answer for why there is a divergence for susceptibility. So that's the topic of my future streams, actually, this article by Rosnagel, book by Gruner, and that's how we can finally understand what is a charge density wave, at least on the level of PhD student. Okay. Let's see what they claim next. Okay, they again claim that it's a special material. It has some electron-electron interaction and electron-phone interaction. Of course, they are there. They are present in all the materials. If you don't know why some properties are present, then you of course claim that it's because of electron-electron interaction or electron-phone interaction, because everything in condensed matter is from this interaction. It would be strange if they claim that there is some magical extra force. Of course, it's very unlikely. So that's an obvious rather statement. Okay. Okay, they have antiferromagnetic ordering. That's what I don't know. I didn't post the question here. I should have posted it. And they have a cited paper, but we don't have a button that downloads all papers. So of course we are too lazy to scroll, find this cited paper, search. That's a disaster. That's not how science should be done. We should have a button, download cited papers. If you are a good programmer, please contact me if we still haven't done it. Okay. And additional superconductivity to this. Yeah, they just repeat what I said, basically. Why do they study pressure temperature diagram? Well, they could study just temperature diagram, but pressure, it's a not trivial parameter, so it's interesting to study also pressure. Well, like, I don't know any good reason why, for applications, why it's important to study pressure dependence. Okay, they repeat the statement from the abstract. They say some commeasurability driven and columbically controlled. I absolutely don't know what it could mean. Well, maybe they mean just this area, and columbically control. Well, I'd better not guess. They will calculate. I mean, this is the plot of their calculation later of the Coulomb energy, but we're speaking about resistivity, so we need to understand how this energy is related to resistivity, and also how this calculation of energy is related to any other calculations. There are like well-known calculations using van der Waals forces of like molecular forces of solids, and this looks very far from that theory, but I also don't know how that theory is used. But okay, it doesn't really matter. And they just claim here some strange statements. It's also not known how superconductivity is dependent on pressure. Most likely it's an unanswered question. And by the way, just to tell you, like here I have all sentences from the new line, because that's way more important to add some comments, but I have bigger spaces between paragraphs, and that's how I make this text not as dense as it's written here. Because you see, like when you read article, then there is a lot of text, right? You just read it and you see one sentence that you don't understand after another sentence that you don't understand. You can't even focus on like writing your focusing on what you think about it. That's why I have developed this application to have LaTeX, such that you can make text sparse and basically add all your questions or comments as I highlight them with green. Okay, let's read what they wrote later. They claim that pressure influences electronic interactions, which is maybe true, but really I doubt that we can still have model of like pure electrons hopping, and just say that pressure changes parameter, because like intuitively I would think that we just need a new model which has some interaction with environment, and what is this interaction is still not really clear, but in scope of this work they claim that pressure changes the parameters like quantum model of the system. And they claim that it's better than disorder because okay, what I guessed, it's because they don't need to rebuild material. They can just apply pressure, then decrease pressure, and that's how you can influence electron interactions. And of course, if you want to add disorder, you need to rebuild the whole material, which is way more complicated. But it was also not clear if the pressure is really if it works as a disorder. Maybe it's a different parameter, so still not clear why do we need to study pressure dependence if it's just one parameter and disorder is just another parameter. Maybe they give purely different physics. Okay, and they also say that there were studies before in pressure dependence changes. I absolutely no idea how pressure induces changes in electronic ground states. It sounds that it's very hard to check this claim, but to have 4 references. So if I build the button that downloads articles, I will tell you. The case of yeah, but okay, that's just abstract, like, you know, typical introduction where they don't say anything really useful. They just review some claims which are famous in this field without much explanation, like discuss pressure, discuss some factors which influence the phase, and discuss some phases that this can happen, that's happened, some examples, of some phenomenon, some heavy fermion compounds. So basically we can just skip introduction because yeah, that's just our general knowledge. That's not something really particularly useful. Okay, the starting point, the first paragraph out of, as far as I remember, 4. Okay, that they discuss the structure of the titanium disulfide. Fortunately, this thing jumped here. It should be actually somewhere here on the starting point. I don't know why did it jump here, but that's the picture of titanium disulfide. Later it will be claimed that they also know not coplanar, which is very expected because all two-dimensional materials, they are slightly not two-dimensional. And also they are on the substrate, but here we have a even layer material, and I don't see anything really informative in this picture, just 2 atoms. That's how they're connected somehow. I'm not sure really what this picture is telling us about. Yes, there is the connection. 1 titanium is connected to maybe 3 sulfide, such that there are 2 sulfides for 1 titanium. Yeah. A variety of phases. Yeah, there are a lot of variety of phases. What is an incommeasured Chernysty wave? Here we don't see it because we work only with this nearly commeasured. So incommeasured Chernysty wave would be somewhere here, but they didn't discuss it in this article, so I don't know what is it. I forgot what is incommeasured Chernysty wave. And commeasured is below 180 Kelvin, and that's exactly this state of the material, which is very resistive state. Yeah, that's what they claim. Then they refer us to some phenomena which they don't explain because that's not the goal to explain it. They just report this result. They have some Fermi surface instability. Well, which is a typical perilous instability. That's exactly it. They just call it in a very different way. So all this part of the sentence, it can be simplified by saying that there's just perilous transition, which is known for one-dimensional system. And somehow we need to just show that this two-dimensional system is approximately one-dimensional system, like effectively one-dimensional. And that's how we can claim that some perilous transition can also be there. Then they say that it's geometrically simplest. Whereas, yeah, and as we see here, that's geometrically simplest because it's homogeneous, everything is just ordered. That's what they also claim here, that this is a David stars. So the question is that how to connect this image. Let's look at it, by the way, here. Here. That's the image, and how we can connect this with this. And I guess that or 12 titanium within layered 13 titanium. So I guess that we just forget about sulfide atoms and say, look, these are the titanium atoms, sulfide atoms maybe on another plane. As we see here, they're slightly on like above or below the plane of titanium atoms. And only titanium atoms are moved to the center, more central titanium atom. Now they claim that this deformation gives the gap, and I don't know how to explain it. I think we need to claim that that's the parallel transition, but I'm a theoretical physicist, so I need to write a formula which will tell me that exactly this gap appears, and right now I don't know, and that's not the article which will teach us and me how to do it. That's article about only this plot. Okay, but the statement is that if we have such distortion, which happens naturally at the low temperature, then we have the gap induced. And if we have a gap induced, then it's insulator, or at least it's much harder for electrons to go to conduction band. And maybe it means that there is low resistivity, but as a theoretical physicist, I'm dissatisfied with this explanation, because the good explanation is the one to which we can immediately write good formulas, and here, unfortunately, it's not explained to this degree. Okay. Then they claim that that's also a Mott insulating state. So Mott insulating state is the state where, as far as I remember, we have not so many electrons in the system. And we have here actually a chat which could help me, but the chat is not working, so let's even not try to use it. Some glitches, but it's not a problem. Some synchronization is broken. It's not also a problem. I got used to the fact that this app is not developed to the good state. Okay, so that's what happens. That they also claim that special physics appears there, like Mott phase in the commeasured, maybe not, yeah, commeasured charge density wave. I still haven't learned what is the Mott insulator, so for me it's just an abstract statement that if we have such deformation, then some model is applicable. They say that there are some other experiments that also confirm this. Okay. And some perpendicular displacement also should be, I don't know if they took this into account or not. And what is swelling is not here, but they claim that some swelling appears of the layers. It's really not clear what they mean by this, but that's what they say, that that displacement occurs not only in horizontal but also a little bit in vertical direction. Maybe it doesn't have a big influence, but to understand it we need to read these articles. Okay, now we have since statement that Mott phase is sensitive to doping, disorder induced by irradiation and pressurization. It's again just a claim. I don't know why do we need it here. Maybe to make this article bigger. Oh, dear love, peace. Welcome to the stream. I was waiting especially for you. So maybe it's not hard for me to make a little summary. So I'm discussing this article from Mott state to superconductivity, and that's the main plot which they got. And right now I'm on the approximately middle of the first page out of 6, so you still can learn a lot of things and you didn't miss much. And you can of course ask questions. That's why I created this chat box here. So if you fix pressure, by the way, I wrote here what is an ambient pressure. ambient pressure is the 1 to the minus 4 gigapascal, and here they have very high pressures. It's not clear why do they need high pressures. What if they went to the low pressures? Maybe they're not interested in low pressures, but okay, that's what they meant, I guess, by ambient pressure. So if you have a very low pressure according to this plot, and if you decrease temperature, then this is the first result. I'm not sure if they got it first ever, or it was obtained before. Maybe it was obtained before, but I don't know where it was obtained before. So the resistivity increases like this. And as I was saying before, there are different phases and different ideas, but the discussion of ideas will be later. So if you stay for maybe half an hour, you will get some explanations of why suddenly resistivity increases and increases, and then again increases. And it's also a log scale, as you can see. And they have some labels for these phases. There is also actually a hidden phase here, but let's not discuss it because it's not written in this article, and maybe it was discovered later after this article was published. And it was published in 2008, just as a reminder. Okay, so that's the crystal structure, that's the displacement of titanium atoms. I also don't know why we are so focused on titanium atoms, not on the sulfide atoms. Maybe titanium atoms are heavier. I don't know. Okay. Let's find out what they claim at the last part of the first paragraph. Phase equally contain David stars. Yeah, okay. There are some comments about this David stars configuration, but we will look at them later because they're also shown here. Yeah, I wasn't reading very attentively before these statements. Yeah, they claim, basically they just give introduction to this picture, which will be discussed right next one, that here we don't have much distortions near these David stars, and David stars are bigger distortion. What is really meant in terms of STM measurement here and here, I can just guess, because okay, here it's explained that this is a symmetric state of all David stars, but here I yet can't imagine it, so I need to read another article about STM measurements. And they also claim that this is a Kagome patchwork. Yeah, like this is just like you know, like when you have some references that you need to add to the article, then you select some claims from it. And I don't know why did they write it here, because they could wrote it like 2 pages after. Okay, let's go to the second out of 4 paragraph, the discussion of experimental results. So these are the same plots, but in different scales. This is the resistivity, this is the temperature on the X scale, and resistivity on Y temperature on Y scale. And yeah, I mean, here we take only a part of it up to the 4 gigapascal. And it's good that I have this image here. It's good actually that I have this app that I can use to display everything, because we really need to look at this image a lot of times, and it's good that it's just stays here, and I will be a lot of times in the future showing it. So we go through all of this range of pressure, yeah, 4 different fixed temperatures, and that's how we obtain these plots. As I said before, I don't know anything about this hysteresis. For some reason it's there. So maybe it's better to look at this plot of resistivity. And by the way, if your teacher tells you that, look, you have so many zeros, why don't you put like 10 to the minus 1, 2, 3, 4, 10 to the minus 4, and have just 1, 2, 3, 4, 5, 6, 7 numbers? Then you can tell him, yeah, that's a good idea, but look, this is the well-known article about titanium disulfide, and they also didn't do this. So maybe it will help you somehow. I don't know why did they publish like this. Looks like a bad idea. But that's how the resistivity is changed for different pressures. And like what to comment? Yeah, no, but you should view it as you go from the vertical side to the bottom one like this, because you change temperature, and temperature is the vertical side. So vroom, 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 vroom. So after you go after like approximately like, yeah, 6, 7 gigapascal, then the change is not such big. And here you also see like the 6, like what 7, and after 7 gigapascal, the dynamics is approximately the same. You just decrease the resistivity, and then bam, it falls to the superconductivity. Yeah, as I said before, this is a distorted plot where superconducting temperature is multiplied by 10, because otherwise we will not see it at all. It's a very little temperature on this scale of temperatures until 300 Kelvin. Okay, they say that based on their method, in which they are assured and which they comment also in the appendix, they got these dependencies of resistivity. Maybe that's what is commented here at the caption to the plot. I just wanted to have a second and read and make sure that I didn't miss some good statement here. So maybe I should say that if you go through this region, like for very, very low pressure, only in this region the resistivity goes to the higher value. But for other pressures, no, it goes to or a constant or then to superconductivity. And that's very interesting and unusual feature, because like I don't know how to explain it actually. I have some ideas which I will discuss later, but that's important thing, that not always your resistivity will go to the superconducting states. For example, for some pressures it can go just to insulating state. As a theoretical physicist, I would like to see a model that describes this, but maybe it's not even discovered yet. I don't know. Okay. Yeah, and they just call labels metallic, Chelsea wave, so on, the thing that I explained before. And they also give some numbers, that this number of pressure and this number of temperature. So somewhere here, this is the place where superconductivity starts. Observe for standard. Here they say that they observe actually I don't know, maybe it's a typo. Temperatures below, it should be below 2000 but not 2500. I think that's the mistake of this article, but everything is around this plot, so here there shouldn't be any mistake. And it melts, yeah, so it should be, I will note here later in my notes that it's a mistake. That's what I have said before. Yeah, again, that's what I already said. That's also I just said. So that's the description of that plot that I just told you, so nothing is missed here. They also say like some words like metallic-like signature, and they don't really explain much what do they mean by metallic-like signature. Maybe it means just the low resistivity, because if resistivity is low, then we claim that it's a metal. But these are complicated words which are not really important. Also, like what is interesting is that like even if we look at the metallic state where resistivity is little, then if we look at resistivity as a function of temperature, then it's unconventional. They don't explain what is conventional, but some using AI assistant told me that conventional superconductivity is this one for low temperature, so it depends as t squared of temperature. Why is it so? I don't remember. If you remember, you can write this in the chat, which will be a nice thing, but it doesn't really matter because some special temperature dependencies here. And I'm skipping this plot because I have already discussed it before. Maybe here there will be some comments and I will return to them later. Yeah, okay, so it's a good idea to comment what happens here right now, because that's exactly what is discussed here. Just I will remind myself what is written in this statement, then I will switch to discussion of these images. Okay. Yeah, so I remembered what happens here. So, okay, first of all, discussion of this picture. So, as it's shown here, sometimes electrons, atoms are displaced and they form the symmetric distortions of the David stars type. But that's sometimes only locally, for example, in this non-Coexists wave phase. And, well, maybe it's not homogeneous, but here it's claimed that it's a really homogeneous distortion. So a very symmetric one distortion is present in whole two-dimensional material. It's interesting to see STM, but we don't have any STM images, so I can't show you them. I would need to search for a lot of for other articles for a long time for them. But these David stars, they appear, then they grow, and here at these pressures and temperatures, we have more David star symmetric states than non-deformed states, and in fully insulating state, we have only David stars arrangement of electrons. And in metallic states, everything is non-distorted, maybe homogeneous. That's what written here, that distortion considerably reduced. And just what I know is that there are actually different versions of distortion, and I wanted to show you an article. Yeah, that's the article of a person whom I know in person. So let's look at some images which he found. Maybe it's not really that article. No, it's not that article, it's the wrong one. I just wanted to show you another options what can be there if this app were fully developed. I would show you immediately. Not this one. Yeah, exactly this one. Now we go. And now we need to close not needed PDF. And then we have this structure of this article. And let's look at the results. And Monte Carlo simulation. So this is the prediction of states when you insert new electron. There could be different states. This is the coloring for the different distortions. And they also have this plot which tells us a lot of what can be in the state. And basically it tells us it's the like plot of configurations that for this amount of extra electrons we have or symmetric state crystal or fully antisymmetric, I mean chaotic state glass or domain state. So that's what I know, and that's why when we see here some symmetric state, maybe we mean that where am I? That we don't have any extra electrons. That's how I explain it, because otherwise it would be very confusing. Let's get back to the article and just believe that there are no extra electrons, otherwise there will be a lot of different phases as far as I understand, or at least we need to check experimental confirmation of that article that proposes us to have a different phases. Okay, that's the summary of what I said. We have again a lot of cited papers. We don't know what is exactly a metallic system. Maybe it's when we have a low resistance. And there is a strange statement that there is also a magnetic field which could be applied and destroys superconductivity, which is not cited. So I don't know why this statement is at all here. And then the last statement out of the second out of 4 paragraphs is that superconductivity is insensitive to pressure and melting of charge order. It's not clear what is meant by changing of charge order. If you know, you can write it in the chat, but I don't know. Measurements insensitive. Yeah, and here we see that if we increase pressure, then nothing changes. We just have superconductivity. Well, they are basically paraphrasing several times that they need a model to describe this physics. And in scope of this physics, you have different phase transitions, so you can post a lot of questions in scope of just one question to describe the resistivity as a function of pressure and temperature. And they also call this phase as a textured phase, because maybe it looks like a texture. Okay, now we are coming to not a really theoretical part, but a part that gives some ideas about the theory. And okay, the motivation is, as I said, we need to understand this paper, this phenomena. And they claim, okay, the first subparagraph is meltdown of Mott phase. So that's the well-known Mott Hamiltonian, which I don't know like very deeply. I know that that's how it looks like. We have type binding approximation, so all sites are fixed, and we have on-site interaction. We have hopping in between sites, between nearest neighbor sites. That's the first term. Second term is the potential. I don't know deep this Hamiltonian. I have a question here, how to derive it. Maybe it's written in a lot of books, but it's not written right now in my head, so I can't comment much. But that's the tight binding model, and maybe it's better not to tell much because we all know, or it's better to say that it's a very popular model, which is a starting point of all condensed matter, that we imagine that there are some eigenvalues of the Hamiltonian, then we go to a basis of eigenvalues, and in this basis we have some creation annihilation operator, and all of the models are in scope of creation annihilation operators. Let's see what they write here. They claim that there are 1 second. Okay, they just comment the origin of these parameters, which are only two parameters, the t and u parameters, and t originates from overlap of electronic wave function, so which is always, and that's the hopping. I can't derive it, but that's a well-known statement. And so maybe this model belongs to only electrons above the gap. That's why we have this u parameter here, because they interact Coulombly, so that's the energy of their on-site Coulomb interaction. It's interesting to note that we work only with materials which with electrons which on above the gap, excited above the gap. So all other electrons below the gap, they sit quietly and just make this material existing and provide us the cell over which we sum. That's, I think, the reason why we say above the gap. Okay. Then this is the place where there are some strange statements where they try to relate this change of pressure to the change of parameters. Okay, later below it will be said that u divided by t should be, as far as I remember, 10 to have a Mott transition, and they claim that exactly this model without any modification should be used to explain this transition, but the only thing is that the parameters are changed because of change of pressure. So that's okay, the claim that they give. Since I don't know anything better, it's better for me to believe it. So let's just think about this deep idea that pressure weakens the potential that defines local wave function. I haven't heard about this ever in course of quantum mechanics, that pressure influences the potential, which is like electrostatic potential, right? And pressure is the heat of extra particles. Of course, they interact Coulombly, but I don't know, like, sounds not convincing, at least just by the statement that pressure weakens the potential of maybe titanium atoms, which are the most important maybe here, or sulfonite atoms. I can't tell you, but here in David stars they say that titanium atoms play the main role, so I guess the titanium atoms also are key for creation of potential that makes electrons localized. And that's how pressure influences U. Then pressure also influences T, which is written above the U. How will pressure influence T? It's really not clear, but some screen capacity is there, and there is charge density wave gap, and like it's not explained at all. Like not explained at all. That's a very bad sentence. I can't understand what do they mean at all. And that's why I said that that's a strange part of the article, because maybe it's so, but we need to have the overlap of wave functions, right? And of conducting wave functions. And I thought it's like okay, it's a localized still state, and then the electron hops from one to another. It's not a Bloch state. And also call them real energy scales. Okay, so there is no way to understand it, so that's why let's just go ahead. The claim is that pressure changes the gap, and if gap is less strong, then wave functions more overlap. How is it written in formulas? I have literally no idea. Okay, that's about the pressure dependence and how this pressure makes Mott phase or charge density wave, commensurate charge density wave phase disappear. Then it's also a good question how Mott phase is different to commensurate charge density wave phase, because here this is the same, and I don't know much about Mott phase, so maybe they're always the same, but I need to read about Mott phase to answer this question. Let's read something about non-commensurate charge density wave phase, this one. It's again a paragraph which is a very not clear one, so that's the summary of what I will be telling you in nearest 5 minutes. That nothing is really clear here, but let's just understand the claims. Main electron systems. So they want to have some microscopic mechanism for domain formations, because yes, there are domains, there is the Hubbard model, which is a microscopic one, so they want to have this domain formation. They really want to maximize the electronic gap. It's absolutely not clear what do they mean by this electronic gap. Maybe it means that it's more, of course, favorable for system to be in the charge density wave state. So when we have this islands of David stars, because yes, that's like energetically favorable, and that's why if there is a way to maximize gap, it will be also energetically favorable, but here nothing is explained. It's just abstract statement about some electronic gap. Why does it need to be maximized? It's also not really clear, because idea is that the state in nature which exists is the one who has a minimal energy, and if the minimal energy in the state which does not have the gap, then we just will not have the energy gap there for example, here, like we have energy gap of very different nature. So, okay, what's written here? Then they say that there are also Coulomb forces that are present in the game. That's why they will be later calculating this plot. That's why maybe it's better for me to comment something, but okay. Maybe this Coulomb force is related to the U parameter of Hubbard model. They also write several times columnically controlled texture phase, because that's the texture phase. But what does it mean by columnically control? Maybe it means that like electrons also interact columnically on top of the hopping from one side to another, because hopping is interactions with the atoms itself, and now we have also electrons. They also have some depletion, like maybe here, I guess this is the gray area where they are really depleted. But let me just place. So maybe the conclusion is that there are these two factors. One is the hopping, other is the Coulomb interaction, which gives also a gap. Why does it give a gap? I have no idea. What is this electronic gap? It's not clear. Maybe gap originates from just the like pairless distortion, and EC is some Coulomb interaction force. And here we are coming to this strange figure where they say that, okay, somehow we need to have these two parameters. We don't know much about this gap. They just say that there is a gap, but there is some interaction of something of in the material, maybe of electrons, but maybe also atoms. So it's not really clear what do they mean by Coulomb energy of what, of total cell or what. Coulomb aspect of this charge transfer. No, I have no idea what do they mean by this, but this some strange aspect is analyzed, and they give us these plots. Maybe it means that there are different layers, and this is like one layer, another layer, and how are they distorted one with respect to another. Stacking domain sizes. So that's my interpretation of what's going on. They have two layers. Each layer has different distortion, and they interact one with another, and that's connected to the change in resistivity in the non-commercial density wave phase. they just don't say anything about the resistance. They say about creation of this phase, which is defined by the resistance. So it should be meant that for the explanation of resistance, we have a system which wants, because of distortion, to have a gap, and then there are some Coulomb interactions of particles, maybe on different layers, which for some reason doesn't want to have a gap appeared. Maybe it wants to break distortion because if I don't know, maybe it drives system to more homogeneous state. That's my interpretation. Just read this. Discommensurations in the textured phase host the electrons that do not fit below the gap that exist in the commensurability ordered domains. So here electrons are above the gap, here they below the gap. Thank you, Mr. Grand Chief Lekko. Or Marina. Thank you. I'm discussing this plot and trying to understand what do they mean this here. I see, Marina. Thank you very much. Yeah, but I'm a little bit stuck because this article is not really well explaining this. So I need to move forward somehow and not really point much some unclear explanations. Okay, the claim is that there are two parameters that influence this resistance, and and both of them are not clear. What is it meant by both of them? Some Coulomb forces and some interaction with the distortion, which gives the gap. Maybe later in the section of the methods they will explain more clearly what do they mean by Coulomb forces. But here they report the ideas about the final result, that okay, if we have these maybe two layers, then what is the energy of the interaction? Like, who cares what's the energy of the interaction? It should give us the resistance. But they draw the plot and they say we don't need anything, we need just this region. Why do they need just this region? Maybe because of counting, but oh, that's very unclear part of the article. Better not to even know this. Yeah, then discuss these differences. Then again, like, why do we need to calculate all of this if you need experimentally just this area? It's a very, I don't like this plot, I don't like this part of the article. It's a collection of unclear statements, at least for me. They call this mechanism Coulomb control phase separation. What is meant by this? It's absolutely not clear. I don't even know how to comment this. It's just not clear at all. And they also have some like sentences which I consider just wrong, that phase is an example of phase separation. Like, there is no way to understand this. It's just a bad sentence. I think they were too lazy to do some like good explanations, so they just gave some ideas and one citation, or is there another citation somewhere? Another citation and another citation. So some citations, some very raw ideas. That's a bad part of the article. Okay, right now what we have discussed the insulating state, the non-commensurate density wave state. So here there are some abstract ideas that pressure influences parameters. Here there are some ideas that there is some special Coulomb force, and this Coulomb force is doing something and then changing maybe this a distribution of electrons to this one, but we change temperature and pressure. So if you want to find out how this energy influences, you need to find a dependence on pressure and temperature. Don't need dependence on stars per domain. It's absolutely useless part of the article. If you disagree, then just write it in the comment. Okay, let's go to this finally third of the three area, and it's about superconductivity. And here we had the charge density wave. Right now we have superconductivity, and that's the first question that arises: that why not charge density wave? Because we had it before, and why now we have a superconductivity? And do we have a superconductivity actually or no, or not? I mean, it's a strange question, right? Because here we have a gap, and here we have a gap. This gap makes a system insulating, and here a gap makes a system metallic. I mean, not metallic, but conducting, right? Superconducting even. Like, I don't know yet right now how to comment this. I'm also really confused also that, like, if we have non-zero temperature, then shouldn't we have a non-zero current? Okay, it is like an abstract question, which I don't really know right now, but I should ask someone who knows superconductivity. That, okay, we'll write myself. Zero, non-zero. Yeah, should the current be zero or non-zero if there is a superconductivity not on zero temperature? Because maybe we should say that there is a normal current. Oh, sorry, normal current and the superconducting current. And if there is normal current, then why not that what? Yeah, then why do we have non-diminishing current? Okay, that's that's what I don't remember. I need to ask just people who are not lost in the field of superconductivity. Yeah, so it's a good question why we have a conducting material here and insulating material here if in both regions we have a gap. But they don't discuss it here. They just discuss why don't we have a charge density wave here. So they jump to this plot, which is obtained at 6 Kelvin, so right above this superconducting temperature. And we go through the pressure. So here we have the insulating phase, then resistivity drops. Why do we need it? I don't know really, but they have Okay, maybe about this compete or coexist, it will be the next subparagraph. But here it's I mean, it's called superconductivity in textured phase. Maybe it's meant here. Uh, uh, Okay, they just describe again this plot that look here we don't have superconductivity and yeah, they for some reason want to illustrate it. It's not clear why do they need to illustrate this point, like which point to illustrate this point, which point. No notable competition. Like, yeah, we don't have superconductivity here, so why do we need to illustrate something? Below that pressure estimate range. Yeah, we explain again what happens on this plot, but now on this plot, which is the same as this plot. I don't know why did they add it here. I should delete these two plots from this collection of main formulas because they just useless. This is strange and explain. This just repeats what happens here. Yeah, we all know what happens. We have our eyes. Yeah, they say that this phase dissociates as it already was drawn here on these images. That's why resistivity drops. Yeah, maybe it's a good thing to see how it behaves, but we already have. I didn't add that picture here to the main notes, but to the main formulas. Okay, let it be here. If people are bored looking here, they can look also here. About 7 gigapascal residual state behaves linear. Yeah, we see it. They say that there is a scattering of electrons on these domains. That's why there are these arrows, because electrons travel, then they scatter, then they travel later. How to describe this scattering, I literally have no idea, but maybe someone who knows theory well did it already. Scatters. Yeah, then they repeat this again, but in a more complicated form, like manifest sensitivity of normal state resistivity to collapse. Like, I mean, it's obvious that it meant that just decrease of resistivity, just too complicated sentence for easy statement. And no formulas are here, so we need to use some other article to deal with this thing. Now they again say that there is electron phonon coupling, because of course it's there, no one will doubt it. Nothing is really informative here. And there is a strange statement that some Fermi surface is affected by Chernysty wave and some of the superconducting transition, which is maybe obvious because we have some electrons which are in normal state, and in normal state they they will be in the they will be trying to go to a superconducting state, and in the Chernysty wave state they are not going to take part in conductivity and superconductivity. It's very not clear what is meant really here. Why same parts of Fermi surface are affected by two transitions? It's an abstract statement which is not really explained, so we don't know what's really going on here. Like, it's not a different part, it's the same part. this is just a bad text, so the only value of the article is that they gave these results, and then they wrote some text which just consists of some complicated sentences without much explanation. Maybe later I will redo this video and tell that there is a sense here, but right now I don't see any sense. Like, just think about it. Some parts of Fermi surface are affected by Chernysty wave and superconductivity transitions, and nothing is before to ground this statement. So let's just forget about it. I mean, know this, but don't think about it, because thinking about it is a waste of time. Some observation was done. Maybe they got some parts of this plot. Superconductivity is not affected by Chernysty wave, but what is meant here, it's not clear. So then they discuss intercalations. I mean, I don't know why did they write some statements. They could not even discuss it at all. What will be, they don't know. They don't know how it is related. Maybe they will suppress Mott phases, but why do they discuss it at all if they did this measurement? It's not clear. So they say that maybe if you put extra molecule between layers, you will be having less resistivity. Why? We don't know why. We don't know why. So what is the takeaway of this paragraph? There is no takeaway of this paragraph. They say that somewhere there, the non-commensurate density wave, they coexist. They don't compete, Chernysty wave and superconductivity, in this area. So it's like this somewhere here. So they coexist. Maybe it's meant about this area. But we don't know, because it's drawn as a purely superconducting area, and here it's a purely non-superconducting area, but it's written that they coexist somehow. Why do they coexist? There is no explanation at all about it. Because same parts of Fermi surface are being affected. Why they are affected? Because both is electron phonon coupling. I mean, that's a really bad explanation. There is no takeaway from it. They give some strange statement that they coexist, but we see that they don't coexist. At least it's not clear how the statement coincides with what we see on their main plot. The only takeaway is that, oh guys, look, that's the plot of resistivity for this line. Then the last one out of methods section, and then finally summary. I mean, of discussion section, the paragraph. So compete or coexist. If you have some ideas about superconductivity and Chernysty wave, do they compete or coexist? Before they wrote that they don't compete. Right now they're asking us if they are competing. Okay, so remember what is written here. It's not an answer at all. It's again a bad statement. That's why I will also write it in my note that that's a bad, again, chapter. First of all, they say that, yeah, as it was already known before, we want to have one theoretical framework which will have a superconductivity and Chernysty wave in it. and they rule out some ideas. Superconductivity is rooted in a manner of so-doped Mott phase. What is it? I have no idea. Of course, we can read cited papers, but we don't have download cited papers button, so we will not read them. Some possibility of self-doped Mott phase. Yeah, like I need also to understand what is a Mott phase, and that's when electrons like repel each other, and that's why they have the insulating state. So sounds like not superconductivity, because Mott phase is a Mott insulating phase. We have a conducting phase. And then they also rule out the spin ordering fluctuations. Well, yeah, like in conventional superconductivity, we don't have any spin ordering. But there are a lot of models of conducting materials, so it's not clear like what is. Like they roll out 2 models, but what about a lot of other models? Maybe one of many other models is applicable to this material. Then they say like, oh, there are other studies, there are similarities to organic layered superconductors. 2 times. So then they give a strange claim that there are 2 gaps. These people are not strong in theory. That's what I see from what is written here. So nothing is answering this question, compete or coexist. They just say that there are 2 reasons for superconductivity that they don't think true, and there are some similarities to other materials of superconductivity. And they say that maybe superconductivity is because of some pseudo gap. What is a pseudo gap? We don't know, but we have some other superconductors which looked similarly to what they saw according to their opinion. So that's why they advise us to just read these articles, and maybe later it will be clear how does it coincide with charge density wave. It's not clear how. Maybe here there is no information about charge density wave, but just they think about pseudo gap. Let's write about pseudo gap, some sentences, and that's all. Okay, finally summary. Summary. There are a lot of regimes in the charge density wave, I mean in titanium disulfide material, and these are the phases, which I have mentioned several times before. There are some differences of this material and superconductivity in this material. So it so there is strange statement of the change of normal state. I don't know how to comment it. We don't know anything about normal state. What we even mean by normal state is not clear. Then they say like, guys, that's a important material, again, as they wrote several times in the abstract or introduction. And then, hey, use some X-ray studies, Raman studies, infrared studies. What do they mean by normal and superconducting state? It's not clear, because here they write just these images. This is not distorted, this is distorted only in this region. Yeah, like we can do STM, maybe it's done. I don't know how it coincides with some other like some predictions. Like for example, here the authors claim that there are different states like glass state, domain state, so on. Maybe it's claimed that this was experimentally confirmed. Right now it's from the theoretical calculation, I mean numerical calculation thing. So it's not clear what they want to tell us to do next. What is the direction for theoretical discovery? The only value of the article is that they measured some resistance, and they read many previous works, so they give their thoughts based on some statements from previous works, which are not valuable at all right now for me. Maybe other people will be motivated to do some theoretical discoveries based on this idea, but not me. Okay, then they say that actually we have measured with this current and this frequency, and these are the device that they use to change pressure. They have some quasi-liquid satellite medium. What is a quasi-liquid is also not clear. Maybe you can Google it. I'm not motivated to Google, I just don't know. And they finish with this strange discussion of this strange Coulomb energy. And they have a formula. Will this formula help one to calculate? No. And I'm really not motivated to think about this these several sentences because I don't see any value of this formula. Yeah, they used it. Let's at least maybe understand what is it written for. Charge related to charge transfer within superstructure. Like what transfer from where to where, from one layer to another, or what? Energy per supercell. So we see a piece of very bad theory. It's a very unclear theory. There is no sense for me to discuss it later because it's not connected directly to the measurement of resistivity. They calculate some strange maybe total force of total energy of one supercell because it interacts with all other electrons. If we have a three-dimensional material, maybe, three-dimensional integrals, maybe we mean two layers and they are in space. So you need to know this configuration of titanium sulfide. You need to know the distributions of the particles. How will you get of electrons? And maybe it's meant only conducting electrons, not the ones that are used to keep this material together. Just to read this. The contributions from electrons from metallic triangular parts should be excluded, and the only contributions that relate gap charge density wave should be included. So they then even modify it somehow, exclude something. Oh, that's the announced previously a long time ago ratio, which gives the Mott transition. And that's just the reason why they get this parameter, which no one cares about here, as 10, because it's present here in the U, so that's a deeper understanding of the U parameter. And they also related to bandwidth from band structure calculations. So in order to understand it, you definitely need to read the 19th paper, cited 19th, and then you get the T parameter, and then you know that this is the value where Mott collapse occurs. That's how you can put T, get U, and in U you know some part, then you can deduce the parameter in this formula. So it's like really not useful, at least for me, theory. I can't use it. It's unclear what do they really mean by it. They just say that, okay, let's calculate that strange expression after some modifications. And then, as it was announced before, which is not clear here, there is some strange screening and electron-electron interactions. Okay, that's the conclusion. I have scrolled, like I read a little bit right now, some statements here, sentences here, and they just comment that this is the formula that they work with. They understand it in a special way, which they comment here, but the general understanding of this formula is not written. So what do they want by this formula at all? It's not clear. Some, yeah, electrostatic energy with some constant which they get from ideas of Mott collapse, because for Mott collapse, if that formula is applicable, then you can know some parameters, and these parameters are related to this constant, which is the only unknown constant here. What is this epsilon r, you can ask me. No, I don't know. It's not written here. I'm not expert in Mott insulators, and I don't know this formula with this special strange constant. Maybe it's a dielectric constant, but there is letter R here, and yeah, it's actually written here, the electric constant. So if you are asked what is the electric constant, you can just cite this paper or repeat this calculation, but it's better to repeat this calculation because I don't see any sense to believe any theoretical statement from this paper. And that's already the next paper, so next time there will be a discussion of different article. Thank you for comments of two people in the chat. So the conclusion, let's just scroll through all of this article. The main thing is that they got this plot that resistivity changes. There are some different phases. There is different configuration of electrons. It can be or non-distorted or distorted symmetrically, or more distorted than non-distorted, also symmetrically, and then fully distorted in a very symmetrical way. That's what they measured. They say that that's like all important material which have different properties as usual. Then they say, oh, that's example of the plot of resistivity. It has different phases. Then there are a lot of other resistivities at different pressures. Then they introduce this plot and discuss this plot. And then there is, and then also that's just a discussion of the plot. Then there is discussion of their ideas, what can explain this plot. They relate it to the Hubbard model, which is written here, and they say that pressure should change T and U. I'm not sure that some good theory can appear from such guidance, but okay. And then let's look again, like here, when they discuss this, they speak about this model, that this model should be applicable. Then if you increase pressure, then these parameters T and U should change. And That's how you can go to the not insulating phase. And in this textured phase, they think that there is a strange Coulomb energy, and there is also a gap, which originates from this distortion. How this gap originates, it's not clear. Then also, what is the Coulomb energy that they really are focused on? It's also not clear. How is it connected to resistivity? It's also not clear. But they are very bothered with discussion of this special Coulomb energy. Why they're not bothered in the superconductivity and the charge like Mott state? Because they just don't want, maybe. Then they discuss that for some reason here there is a coexistence of charge wave and superconductivity. However, we don't see it on the plot. But instead of explaining this, they give us the plot of the decreasing pressure. Now we can see explicitly what they mean by these colors, and basically nothing is really useful in this plot. And that's why I don't remember what's written here, because remember that nothing is really important. Yeah, hysteresis is not explained. Islands are not explained. They just say that electrons travel, then they scatter, and that's why there is resistivity. And the same parts of Fermi surface are affected, as it's written here, affected by both transitions. What is meant by this, no one knows. Again, they just say that they coexist because they want to see it this way, and that's the resistivity, and some comments. Then they finish by saying that there are two models of superconductivity that is not present there, but they like the model of pseudo gap because something is similar of this superconducting state and some organic superconductors. That's why they suppose that maybe some pseudo gap can be there, and maybe the model of pseudo gap will unite charge density wave and superconductivity. However, it's not clear what do they really mean, because here we see clearly a phase separation. And also that's a bad plot, which has strange rescale, like they changed the superconducting temperature, just multiplied by 10. Haven't seen anything like this. And in summary, they say that that's the material, it has different phases. Yeah, and maybe you can do some other measurements for some reason. And that's the wave measurement, and that's the strange formula for Coulomb energy, which they really want to calculate, then to compare with the gap. And they don't know the gap, so they just say, oh, okay, there could be different options, what can be. Okay, so that's the nice stream about oh, I forgot to put the disappearing messages here, yeah, in that chat. But we have finally successfully discussed one nice article, which is important for titanium disulfide material. Right now we know how it resistant changes, and that's the main value of this article. Before I would not be able to derive it theoretically. Now I'm not also able to do it, but I have some ideas about theoretical connections and about like experimental results. So maybe one day someone will derive these properties and we will say that we have a really good theory of condensed matter. But right now we just know that there is such material with such good properties. So thank you for your attention, dear two viewers. But if you have some questions, you can just write them to the comments and I will try to reply. Bye-bye.